and I am a course advisor for ECT. Welcome to today's webinar that will be hosted by Dr. Shaalan, who is our industrial automation lecturer here at ECT. And I would just like to turn your attention to the notifications and the sounds. So if you could just turn those off while the presentation is going on, that's just to minimize any sort of interruptions that may come up while the presentation is going on. And secondly, please note that there is a Q&A box, so you can type in your questions there if any may arise during the presentation, and Dr. Shaalan will be able to answer your questions closer to the end of this webinar. So if you do not have the Q&A function on your Teams, then please feel free to use the chat box. And as I've mentioned, we will answer your questions closer to the end of the webinar. So for this webinar, because it is a technical webinar, there will be a certificate of attendance, and you'll also receive a copy of the slides as well as a video recording of this webinar in your emails. When it comes to the copies of the slides as well as the video recording, you will get those in 2 business days from today, and the certificate of attendance will be sent to you 4 days from today. So how this works is that you will scan the QR code at the end of the presentation, or you can just copy the link, which I will provide in the chat box closer to the end of the presentation. And then you'll fill out a short little survey, and that survey will ensure that you receive the certificate of attendance, the slides, as well as the video recording of this webinar. So just to give you a little bit of information about ECT and what we're all about, ECT is an engineering specialist, and we've got industry-driven programs, and this institution offers UK recognized education, and that's all made possible by our lecturers and our instructors who are specialists and professionals in the field of engineering. We also do offer a unique delivery model, which is what basically sets us apart. Now, for this event, I would just like you guys to follow my instructions, and so we can have a seamless and smooth presentation. So today's topic is the basics of SCADA and PLC systems, which, as I've mentioned, is presented by Dr. Abdul Shaalan. So Dr. Abdul, if you don't mind, you can take control and take it away. Thank you.
Amazing. Thank you so much, Komo. Hello, everyone. Thank you for attending this webinar. It is good to see lots of people that are enthused about the topic and would like to learn more or to get a glimpse into different technologies, different systems, and improve on their knowledges. So to start with a little bit about my background, my name is Dr. Abdul Shaalan. I'm the program leader for industrial automation programs, undergraduate and postgraduate levels at the ECT. Where Komo highlighted, we deliver a very interesting model focused on electrical and industrial automation. Our main target and the working professionals and the people that are focused on what they want to do and if they want to pursue that specific path. I have a bachelor degree in mechatronics engineering, and then a master's in engineering management, a PhD in automation systems and maintenance practices in the advances of Industry 4. I oversee the entirety of the program, make sure that everything is up to standards and the students are getting the knowledge and experience that they're looking for, and they are always ready for industry whenever they graduate from the ACT. As Komo said, what we do deliver an online model which basically try to accommodate everyone's needs and everyone's situations and circumstances. You don't have to attend the classroom per se, rather than you can attend all the classes online, and everything is recorded, which you can review at any point in time in case if you missed any of the classes, which is different from how it is with a normal university. We follow a specific or interesting assessment strategy, which combines lots of different experiences. We always try to focus on developing your own soft skills next to the technical skills. So it's not everything about exams, rather than it is about how can you communicate with people, how can you report writing, how can you present, how can you work in a group, how can you approach problem solving, how can you approach problems within with a correct mentality in problem solving approach. And to start with, without what the ACT is, what we are going to talk about today is going to have different cases. So we are going to look into the history of industrial automation, the impact of industrial automation, how automated system works, and we are going to have a brief or a discussion on how the programming takes place. So to start with, we have to start from somewhere, and we have to go back a little bit in time and go back to the history of PLC. And for who doesn't know what is a PLC is, we are going to talk about what it is really. So let's go back in time and let's think about how things used to be made. So if you started to go back hundreds of years ago, everything used to be made by a person, and that person is specialized. He's experienced in his or her field, and what they use tools. And these tools can be anything really. So it can be a hammer, it can be a chisel, it can be whatever it is. And then based on their skills and their own power, what they do, they drive these tools in order to make the products that they want. So their own skills drive the different tools, start to or out of a piece of wood. So basically, that's the same thing with all the different professions. So such a way of operation will have its own limitations. Really, you can't really do much of a complex products only using your own power and only driving basic tools. And this is when the industrial revolutions came around. So first industrial revolution came around with the fact that, well, instead of using that person or that crafter own power, let's use an external power source. This is when we started to use steam engines, and these steam engines were the drive behind the first industrial revolution. Now we started to have that massive power source that we can still drive with our own skills, but it is an extraordinarily much more power than the manpower, and we started to be able to make different products with a larger scale products. With that introduction, it came around the introduction of the transportation or the development in the transportation system. So we started to have the railways, so the steam engine or the steam train. We started to have the steam ships that can sail around the globe instead of just using air or the sails and the air power to drive it. So things started to develop a little bit more. And with this, we started to look into, well, how can we control things in a little bit better way? And this is when we started to have the development. I don't know, it's changed. And this is when we started to have electricity. And the production line. So instead of having just one person making one product at the time, we started to have a stream of different processes lined up together in a production line format, like how it is with car manufacturing processes, because Ford actually was the first one to introduce production lines. With this, we started to have massive increment in capacity. So we started to be able to produce many more or much more. So in alignment with approachability and the development in railway and the shipping industry, we started to reach different people, different continents, different cities. So the manufacturing industry started to boom. Now that carpenter or that crafter, whoever he is or she is, they started to have much larger customer base, which was quite. And with this, we started to have different complexities. Because when you start to see how could they manage to drive a long production line with only electricity, we started to look into, well, that was used or that was developed or made possible by using something called the relay room. So the relays are, in general, these are automatic switches. So think about the light switch that you have at home, and instead of you using your finger to flick the switch, it is using another electric signal in order to make that flicking mechanism. So instead of your finger that is turning the switch on or off, now you have another on top of it electric circuit that is energizing the on or off connectivity. So think about it as two circuits on top of each other. So this is kind of a typical look of
Dr.
how
Shaalan,
a relay. Yeah.
sorry to interrupt you. We getting messages stating that the sound quality, I don't know if it's the sound, but I assume it's the internet that's a bit like it's lagging. It's making the audio sounds choppy.
Right. Okay, that is interesting. Let me try to change this. Okay, can you guys hear me better now?
Yeah, just continue. I'll let you know if anything arises.
Okay, so well, sorry for that, guys. It's yeah, technology problems as usual. Again, if there is any issues with the sound, just please let me know. Okay, so maybe a little bit of recap. So we said that, well, we started to have, yeah, okay, that's good to hear. I hope it lasts this way. So as I was just saying, what we used to have these production lines. And these production lines were just long lists or long arrangements of different processes that are connected together. And these different processes they can be much longer or they can be a lot. So with this, we started to see that, well, how can we manage all of these different processes? How can we manage the timing between all of them? And how can we operate everything together in one go? All of this is still before the 60s. So what you can see here in this photo, this is what a typical control room used to be. So this is called a relay room. And that relay room, what it used to have wide range of relays. And these relays, if you don't know what they are automatic switches. As I said, think about the light switch that you might have at home. And instead of you using your own finger in order to flick the switch on or off, you are using an electric circuit on top of the actual switch to manage that on or off operation of the internal connection. And this is what used to happen. So think about the diagnostics or the changes or improvements that needed to be done to such a room. It is going to be difficult. If anything went wrong, you have to go through quite an extensive diagnostic operation in order to find out, well, which relay was it the faulty one? Was it this one? Was it this one? You can use diagrams, you can use lots of different things to support you, but it is still a very lengthy, hectic operation. And if you wanted to do any upgrades or any changes to that production line, that is a totally different story. Now you have to rearrange everything and change the criteria and the characteristics of all of these different relays. So things are not that easy, things are much more complicated and difficult to manipulate. This is when the 60s came around, and with the 60s, we started to have the first computers, and this is the first smart computational device. And with the introduction of computers, we started to have the first PLC. What is a PLC? It's a programmable logic controller. So it's all working based on the microcontrollers and microprocessor concepts. So what is a microcontroller or a microprocessor? So a microprocessor is a computational device. Think about it that, well, you have a room, and that room is full of, not one room, but think about, for example, well, a university. So that university has many different rooms. So these different rooms have different capacities. So a classroom that has 8 chairs, for example, this is called 8 bits registers. And these 8 bits, or these bits, are micro switches. This is what I think after all of these different news and all the different things and the attention that the news is given to the semiconductors, I think we all know now about all of these small tiny switches and the 3 nanometers and 6 nanometers and all of these different technologies. So it is all about that, well, I have an arrangement. Let's make it in a little bit bigger way. So this is a microcontroller or a microprocessor. The difference is connectivity. Many different rooms. Each room has a capacity. Typically would be 8 bits for the standard small ones. And each of these bits can either hold the value of 1 or 0. So, and this is the switch. So if the switch is off, it's going to give you a value of 0. If the switch is on, it's going to give you the value of 1. And that's why there is a binary system, or the binary numbering system. So the representation of 1, 1, 1, 0, 0, 1, 1, for example, this can represent a specific number. And the reason that we have a binary system is that we can interfere and we can communicate with the internal registers of any microcontroller or a microprocessor. So when you load these values into a specific register inside a microcontroller, what you get an arrangement of on and off switches. And that is the whole principle of why do we have a binary system and why things or how things are happening. So such arrangements will indicate a certain number, and certain number can later on be indicated or can indicate a certain operation, whether it is a mathematical operation, for example, for addition, subtraction, multiplication, or division, which are the main things or the main concepts behind any computational device or any smart device. So the difference between a microcontroller or a microprocessor is the connectivity. For a microprocessor, like what you would have with your computer, what you know that, well, you are going to buy Intel i7, i9, whatever. So you just get a chip with lots of different pins and you install it on your motherboard. So the motherboard is the breakout board. This is where you can have all the connections for the USB and the audio and the hard drive, etc. So it is just the microprocessor is just the brain. But for the microcontroller, you have a chip, and that chip has the connections and the pins and the storage mediums and everything at one device. So that's why that's the main difference between both of them. So for a microcontroller, it's much less computational power, meaning that it has less number of registers and smaller number of bits inside each register. And the reason behind that is that because, well, the microcontroller is not made really for a very complex computation and applications. So it can be used for your microwave, for your washing machine, for your basic devices that are running at home. But for the microprocessor, well, it's a lot of power, and it is used on your PC because mainly, for example, as a basic thing that it needs to do is to control your monitor. Your monitor is made out of thousands of pixels, and each pixel needs to be controlled individually for the colors. So in order for each pixel to have a specific color in order to get the picture that you are looking at, and the transition between all of these different colors and the smoothness, all of this needs much bigger, much more number of rooms to make it simple, and much larger size of registers. So what happened is they took that microcontroller, because again, it's not much of a computational power, rather than the whole idea of managing a production line is like a traffic man. You want to manage the process flow. So what you can see here, this is the very basic, or the very first PLC, programmable logic controller, that was developed in order to control a production line. What it is a microcontroller inside a box. And that is just to make it more industrially aligned, so it can withstand any harsh environment or anything that might come up within the industry or from a manufacturing industry or a manufacturing environment. So in addition to this, instead of interfacing with this microcontroller with the basic programming languages like C or C++, for example, as basic languages, now different companies developed interfaces which are easier way in order to program these PLCs. And that's why you would have now programmable logic controllers languages with the IEC 66 something, not on top of my head what is the standard for it, but it is a more of a graphical way of how can you control it. What you can see here, this is a modern version of the PLCs. So what you can see here, this is an Allen Bradley Micro 850. So AB Micro 850 PLC. What you can see that, well, it has the capability for Ethernet connection, which is a development from older generation that were not able to connect using any modern communication devices, which was very bad limitation or big limitation for connectivity. You start to see that you have two rows. One row is the input card, and the other row is the output card. All the different inputs that you might want to have, because it's all about what you are having here. You are having a brain. You as a person, you have a brain. Without all of your senses, without your eyes, without your ears, without your nose, without all of the sensing elements that you have, the 5 senses that you have, as inputs, you will not really know, or your brain will not be able to function. It is just the brain. It needs different input systems. It needs the devices that give it the surrounding environment knowledge. So that's why your eyes can see and can tell your brain what is going on, what is in front of it, what is it daylight, is it night, whatever. Your nose can give the sense of smell. The brain is the processing unit. And then you have the output side, because if you as a person, you have all the senses, but you don't have any limbs, you don't have any hands or legs, well, you can't do anything. You can't move, you can't apply any force, you can't navigate. So again, you're just processing data and not doing anything. So again, you need an output side. If we translated this into industrial context, what you can have for inputs, all the different sensors, a proximity sensor, a temperature sensor, a pressure sensor, elevation sensor, whatever the different sensors that might exist and suit your application. And from the output side, what you have the different actuators. So the actuators can be mechanical actuators, electrical actuators. It can be pneumatic actuators, hydraulic actuators, all of the different devices that can apply forces in different ways. So this is basically how a full system can be constructed for industrial automation. What you have a brain, you have an input side that have all the sensors, and maybe as well buttons, as it can be just buttons, start, stop buttons, so digital devices, and it can have any type of actuator that it can control. We will look into what are all of these types of actuators in general. So looking at today's applications that requires high level of control capabilities. So what you get, or this is the idea of what you get with a PLC. With a PLC, the idea of having a PLC, beside the fact that you now removed and got rid of all of this control relay big room to control everything without any intelligence, now you started to have the ability to do addition, subtraction, multiplication, all the arithmetic operations. Started to have data comparison, so you can measure or compare data, two different data, temperature, for example, if it did increase over a certain limit, if it is equal, greater than, less than, etc. Word manipulations like copy and move different things, communication and sending and receiving messages between different devices, like how we've seen with the PLC. You have all of this, now you have the Ethernet. In the past, it used to be serial communications. We're not going to get into this, but the ability to communicate, the ability to send and receive different data. With all of this, you started to have the ability to have sequence of operations. Now you started to have the ability, if it is a car manufacturing plant, for example, so for the body shop, let's say, as an example, for the making of the chassis. So you need the base of the chassis put in first, and then the side of the car to be placed in. So if we have one side of the car, I'm so bad with drawing, so this doesn't even look like a car. So the side of the car, and then the other side of the car, and then the bonnet, and then the back side. All of these are processes. So this is a sequence of operations. And this is what the PLC does. It manages that sequence of operations. So you can apply this to any manufacturing process, anything that can happen. If it is oil and gas, if it is the manufacturing of subsea cables. So you have different cables that are laying around in an arrangement, something like this, and you want everything to be pulled in to make the final bundle of all of these cables together. And this bundle can have gas line, electric line, communication line, fiber line, anything. So it is generally, when you're looking at subsea cables, you have a bundle, big thick cable, and that cable inside it has different cables or different tubes with different arrangements, different sizes. So this is how it's made as well. It is a sequence of operation of feeding all of these different cables together, and this is called umbilical machinery's production. So you're getting everything together and tightening them up, wrapping them, securing them. All of these are different processes that happens after each other. So again, this is an example. Food and drinks, anything. It is all the different industries that you can think of. And this is the power of the PLC. And in addition, when it comes to changes in the process, simple and easy, because now you can just go into the program of instruction, which we will have a look at, but you can just go into the program that you created, adjust it however you want. So it can accommodate different processes, changes that you might want to happen or might want to do. So this takes us to what are the different types of data a PLC can manage. In general, what you have either digital or analog inputs and outputs. I/O means inputs and outputs. We discussed what are the inputs, so it can be anything really. So a sensor can be a button, whatever. Outputs, again, can be a motor, it can be a fan, it can be anything. So when we say digital, it means that that device has only two states, either an on state or off state. So like how it is with a button. So the button can only be turned on or turned off. So this is a digital device. If it is a switch or a mechanical switch that it is installed on a machine, if it is a proximity sensor, it has only two states. It's either detecting an object or not detecting an object. That's why it has only these two states, whether it is a 0 or a 1. If it is off, so it's a 0. If it's on, it's a 1. There is nothing in between. When you look at the analog side of things, analog inputs and outputs, if you're looking at the analog inputs, so all the different sensors that you can think of that can give you variable inputs, temperature, from a 0 to 1,000 degrees Celsius. If it's a pressure, if it is, as I said, elevation, if it is vibration, if it is whatever the type of sensor that you might think of. So this is an analog input. For an analog output, so think about controlling the speed of a motor. So you don't want, if it is a digital motor, so you want to turn the motor on or off. But if you want to control the speed of that motor, so again, now you can have that analog output ability to control the motor speed. So how can these PLC be programmed? So as I said, the PLC is just a microcontroller in a box. But in addition, for the basics that the microcontroller can only be, the basic language for any microcontroller device programming is assembly. So this is actually the only language that any smart device can understand. And the assembly language strength, the whole of the assembly language idea is that, if you remember what I showed you, that the microcontroller is made of, or microprocessor, made of all of these different rooms. The assembly language interacts directly with all of these different registers and all the specified bits inside. So it talks to that specific switch to turn it on or off. So that is the assembly language. But it is very difficult to write a complex program using assembly because it is basic. So it takes a long time and very long program to write an effective project or a program with assembly. That's why the more languages were developed on top of the assembly language. And mainly what we have started to have the C and the C++ languages as main languages for interacting with microcontrollers and microprocessors. So when you write a program in C or C++, it gets translated internally into an assembly language and then loaded into the microcontroller. So don't think that, well, I'm writing a program in C, the micro doesn't understand C or C# or whatever it is. It only understands assembly. But you have a compiler, and that compiler will compile your program in C and change it, translate it into assembly, and then send it to the microcontroller. But engineers don't like programming, and that's why a graphical way of programming PLC was developed. And that is the standard IEC 61131 that I mentioned at the start. So what it is just a easier way of programming PLCs. So it has two main branches. So it has graphical languages and textual languages, because, well, some people might still be interested in using higher level or programming like how it is with the C and C++ and C# to program the PLC. But mainly you'll find the majority of the ones that is getting used is the graphical ones. And within the graphical, you have three different languages. So you have the ladder logic, you have the function block diagram, and you have sequential function chart. All of them are similar, but they are different in their operation. So function block, for example, it groups multiple operations together, so it makes the program much easier, much neater and tighter if you have a big project. Ladder logic is the very basic form of graphical programming language. So it's easy, simple, straightforward, but it can take a long time to use if you have a complex project. For the textual languages, you have structured text and instruction lists, and they are quite similar for how it is with the C and C++. They are not C and C++, rather than it is similar flow of operation to them. So now we spoke about the PLC, how it works, what it needs, and the side of things that one side would have inputs and the other side is going to have outputs. When you talk about the outputs, and we said that the outputs can be any sort of actuators. So what are the different actuators? So I said there can be electromechanical actuators, you can have electric motors, or you can have, and this is very commonly used, you have pneumatic systems. And the pneumatic systems are systems that are working based on or using the air as the main power source. This is what you can find at all or majority of the manufacturing assets that exists within life. So any automated machinery that you might find at any factory, you might find, or probably, highly probably, you will find a pneumatic system inside the machine that can manage the transition between different operations, or can do the transition between different operations within that machinery. If you have a pick and place system, for example, that is pneumatic. If you have a wrapping system, if you have filling beverages or Pepsi or any juice filling system or automated machinery. So again, it is mainly handled internally with pneumatic systems or pneumatic processes. Because think about, for example, if it is about juice filling machinery. So you have a carton of juice and it goes on a conveyor belt, something like this. So it goes in and then maybe it is closed. So you need to open the lid of this carton. So it will go here and there is going to be an arm or let's say it's called an arm, something that can flick it open. So you are going to have it something like this. And then it's going to move on, and then it is going to have a filling head of that juice. So that filling head is going to go down to that to the inlet of that carton to fill it up, and then go up again. So this process of going up and down, again, this is pneumatic process, and then it has to be closed. So another arm is going to close the lid back on. So again, close the lid. And then it is going to move on and then picked up and put on a different conveyor. So you might have a clamp, this, that will pick it up and then move it to a different place, a different conveyor belt or a different stack to put it all together in one box. All of this happens using pneumatic power. It is clean, it is easy to manipulate and easy to construct and control. And that's why it is heavily used in industry. But how a pneumatic system is built. So what you can see here, you can see the basic circuit for a pneumatic cylinder. This is a double acting pneumatic cylinder. So if we have a cylinder like this, and it has the arm that extends and retracts, how does it extend or retract? You have an inlet port. So go back in here, you have an inlet port, an outlet port. So, and they can be switched or they are switched. So if I want to extend that arm, what I'm going to do, I'm going to allow the air to go from this port. So it can apply for that arm. It has a disc shaped inside the cylinder. So if it is in the retracted position, so if we have another one here, and we have the plate in here, and this is our arm, and this is our port, this is the extraction or the other port. I want to extend this arm, I'm going to let the air go in through this port, so it is going to apply the air on this plate in here, so it is going to push the plate out, so it is going to get to that state. And this port is going to be an exhaust port. So it is exhausting all the air that is inside, not just trapping and compressing it. And then if I want to retract it from that position, let's have another one going in here. So if it is now extended, if I want to retract it, so I'm going to allow the air to go through here and this port to be the exhaust. So it applies air here, drive it back, and the air is coming out of this port. So this is how a pneumatic cylinder, in a very basic way, double-acting pneumatic cylinder operates. There are different ones. A single-acting cylinder that retracts only by using a spring, so it only has one port, but just for the sake of clarification. So how can we manage the control of that inlet and outlet ports? And this is what happens, or what gets done, by using something called directional control valves, or DCV. So the directional control valve is a device, and that device has multiple switching operations or multiple switching states. What it is connected to, well, so if we just ignore these at the minute, so it is connected to a source of power. And this source of power needs to be directed either to this direction or to this direction. And this is what the DCV does. Based on a signal that comes to it from either of the actuation ports on the sides, it is going to decide whether to have the flow of the air to go through this left port or left hand side or the right hand side. So where it takes or where it gets that signal from, it gets it from the PLC. So the PLC is going to give the signal for the actuation processes. If you want to extend the cylinder, for example, so you want this port to be the direction for the compressed air to go through. So this is when you start to have, well, the PLC is going to have a signal to switch the position for that extension position. So it will allow the air to go through here, and it is going to get the cylinder to extend. And it's going to open this port to be an exhaust port. This is what you can see here. And if it is the other way around, so the PLC is going to give the signal to shut this one and energize the other side that is responsible of this side of operation, so it can retract the cylinder. And this is when it is going to turn this port into an exhaust port, and this port to it's going to be connected to the main power supply, main air supply. So the cylinder will retract. And this is the fluctuation between the different positions. Technically, how that DCV symbols are presented is like how you can see it. This is what you can see here. So this is how the symbol for a DCV can look like. So this is a DCV, this is another one, and this is the third one. So a DCV can have different status. So it can be 3/2 DCV, 5/2 DCV, different actuating positions or different actuation power. So for example, what you have here, you have, just to make it larger, I'm not sure if you can see it properly or not. So something like this, something like this. What you can see here, you can see differences in the two actuating positions. So this is an actuation position, and this is another actuation position. For that actuation position, it is directing the air to the right-hand side, so it can be, or it will go through this port, and it is going to retract the cylinder. And for that port in here, which is this one, it is going to be directed to the exhaust. For that actuation position, it is directing the flow of the air to that line in here. So it's going to extend the cylinder, and the port is going to be connected, or the other port is going to be connected to the exhaust. So it is going to exhaust all the air from inside. So that is typically, how could it look? They can have different shapes. So other ones can have 3 different states, for example. So one of them have initial all blocked ports. So without doing anything, all the ports are blocked until you actuate it. For this one, the cylinder, it's either fully extending or fully retracting with the main power connected to one of them. So it is holding the position or holding the air supply at one of these positions. For that one, 5/2. So this is going to be, for example, as this arrangement, and there are many of them, have a look, Google it or search it up. You will see that, well, one of them is going to be like this, the other one is like this, like that. So that is a different position. How it gets actuated, as I said, you can get a signal from the PLC. So something from the side that can tell which actuation position to operate. Sometimes it only has one actuation position from the PLC, like how we can have it here, and the other side is a spring. So if it did lose the signal from the PLC, the spring is going to return it into another position. It can be not just controlled with any automation at all, and it can be manually operated. So purely pneumatic system. So manual push button that can be pressed to activate it. Again, different shapes, different times, different shapes and types of how all of this can be done. So this is the circuit of how it could look like, again, for when you are building the system. So that actuator that flicks it between the different position, it is usually a solenoid. So the solenoid is a device that it is mainly a coil, and inside that coil there is an arm, or there is a pin. When that coil is energized, creating an electromagnetic field, it will eject that pin out. When it ejects that pin out, it works as a cylinder, but it has very limited power and limited distance, etc. But it is enough in order to be able to actuate the DCVs. And this is what you would have here, for example, as solenoid A and solenoid B. You can add more intelligence to it. So if you want, for example, to have when the cylinder is extended to be red, and when it is retracted to be green, green light to illuminate, again, all of this can happen because you have that connection to the PLC. The PLC is going to give the signal for the cylinder to extend, which is going to be through a solenoid, and at the same time, it is controlling a light, something like this, that can energize and give the signal to both. For the red, the PLC, so if you wrote it here, PLC, it gave the signal to the solenoid to extend, and in the same time, it did energize that red LED. And if it did give the solenoid a signal to retract, it will turn on the green light, whatever you want. So this is all made possible with the PLC. You can add more. So you can add a horn, you can add a sound or a buzzer, you can have an emergency stop. All of this can be added to the exact same circuit, and all of this can be controlled from the exact same PLC program. When you want to see how the programming of that PLC for the ladder logic works, it was built based on the concepts and the understanding of electrical engineers as well. So in a very basic way, if you want to connect your bulb at home, so what you have the positive line and you have the ground line. And what would you do? You want to connect the bulb in between. So it is going to be something like this. This is your light. When it is connected between the positive and the negative, it's going to turn on. That's exactly the same principle for how PLC and ladder logic works. What you have here, you have a ladder logic program. Think about the left and right hand side column as these are the energizing powers or the energizing line. If anything in between connected, it is going to be turned on. And if you wanted to have a button, which the button basically it cuts a signal or connect it, this is when you can have something called contactor, or not contactor, input. It's an input. So if you want to have an input, something like a button or something like a proxy sensor, for example. So the whole idea of it that it will cut the signal or connect it. If that button is pressed, this connection is going to happen. If the button is not pressed, the connection does not exist. And connected to the same line is whatever the output that you have. It might be a motor, it might be that solenoid to extend or retract the cylinder. So based on that arrangement, if you have the button or the contact closed, so you have a connection here, so everything is going through the coil, which this is the terminology for an output in PLC. You will have a coil, which is, let's say, a motor. So you have a full connection between, let's say, the positive and the negative side, so it will be energized. If it is not connected, that button, and it is disconnected, so there is a cut in the power between the positive and the negative line, so there is not going to be power to the motor, so it's going to be off. And that's the same principle. This is how it works. So in a basic way, this is how it is with the PLC programming, with the PLC structure, etc. And this is how you can start to monitor how things can be done and how can you construct different logics, really. So within that PLC program, you can add different blocks that are responsible of different operations. So these blocks, typically within PLC, what happens is you can have timers, you can have counters, you can have all the arithmetic operations that you're looking for that can apply in mathematical addition, subtraction, comparison, etc. And within the PLC, if we went back quickly to how it is with this one, what you have here, if you noticed, you have on this side here, you have a screen on this PLC. That screen, not a screen, it's just mini LEDs. These ones at the top, they reflect all of these inputs for the PLC. If they are on, they are going to light up. And if they are off, they are going to be off. So these are all numbered 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, etc. for all of them. And the same thing from the output side. So 1, 2, 3, 4, etc. If the PLC, if that specific output is on, you are going to see the corresponding number lighting up. If it is off, you will see that the corresponding number is turned off, which gives a good indication on how it is, indication on what is working or what is energized or not. So what we spoke about here is just this layer for the control or the automation hierarchy. This is the control level. So to start from the zero, the field level, these are all the sensors and actuators that you might have. This is what we mentioned, how they are all controlled. They are controlled in the control layer with a PLC. So what if you have many different machineries in the factory, 10, 15, 20, 100 machinery in the factory, and you want to monitor all of them, and you want to have the ability to change maybe main parameters, not in depth technicals and health and safety parameters, etc. But you want to change the parameters for each day's operations. This is when you go higher level into the SCADA system, the optimization level. This is where you usually see that there is a big room, and that room typically in a higher elevated place, and many screens, and you can look inside and you can see on all the screens all the different data for all the different machineries. So from one place you can monitor what machine is working, what state it is, how many did it make, what are the parameters of it, if you want to change them or do whatever it is. Again, you can do all of this from that one place. So you don't have to go to every single machinery to check on it or to change parameters for operations about it, etc. So up to here, all of this is machinery and technical levels. You start to go higher up, you start to go into management a little bit. So plant control level, which is the production level, this is when you start to plan for the day production, and you start to have a planning and scheduling elements. And then you go higher up level, this is the top level, MIS, and this is when you have corporate level that have supply chain, that have production, that have employees, that have all the different relevant elements for that company under one umbrella. So this is the typical 5-layer hierarchy model for automation systems. All of what we spoke about today mainly was about the PLC and how it works, and about the field devices and how the different field devices work. Each of these different field devices is a spectrum. You get into the instrumentation side of things, all the different sensors and their criteria and how do they operate and how all of these different things can be done, which we are going to discuss on Monday. So if you are interested, or if you did like what you hear today, try to join on Monday. You are going to hear a little bit more about the sensors and the different measurement devices. So that will be it for today. I hope that was useful to you. I hope that gave you some good insights into what is industrial automation, how the PLC work, and how the control in factories can be done and operated. So it's time now. You're welcome, Como. I think we have a couple of minutes or a few minutes. If anyone have any questions, or anything before we wrap up?
So we've got a question from Ranal Ritesh Prasad, and they're asking, do you have someone who can supervise wind energy thesis? Are
It
you
depends on what you are. Well, it's not in the ECT at the minute. We will start a PhD programs or the PhD programs soon, but it depends on what you want to do with the wind energy. So is it design related? Is it control related? Is it performance related? At the minute, maybe the best option would be to go through EIT, which they have an operating PhD program, unless you want to wait until we start our PhD program, which is going to be soon, hopefully within a year time. But yeah, maybe if you gave more context, I can tell you more, or you can have a look at the EIT website that can tell you and guide you through who can help you with this.
Thank you for that. And then the next question we have is from Shikanga Enoch, and they're asking the difference between remote terminal unit, I suppose, and PLC.
If I'm getting your question right, so remote terminal units, these are the remote I/O cards that usually gets installed. So you don't need to have, or you don't have, or you don't want to have all the different, or you don't have all the different inputs and outputs in the same place, and you want to have different connections or different devices that are further apart to connect to the same brain or PLC. This is when you have remote cards or remote IOs. So the remote IOs is wired or wireless IO card that connects to a specific machine and sends and receives the data to a centralized PLC that can control that machine, if I'm getting your question right. The Monday webinar on the website,
Sure.
I believe you can have a link.
Yeah, they can register on the website, but I will provide it to them now just shortly. 2 seconds. So in that vein, for all our webinars and upcoming webinars, you can check on our website. We always have a list of the webinars that we will be hosting. So you can always just go to the website, register there, and then you'll be sent communication about when it starts and so forth. But I have now just provided the...
Well, the Monday webinar is about sensors. I'm trying to read Moses' question. Well, it's all about fault diagnostics. So you have to go through the whole process from the start to end, Moses. So you start with the devices. So the solenoid, is it actually working by itself or not? So it is all about, well, can you test that solenoid separately in an isolated environment to see if it is operating or not? And then you have to find out if it is working how it should. So you move to the next step, the connection between that solenoid and between, you will have a terminal block, and probably you're having a relay in between, and then you have the connection to the PLC or the controller that you have. So all of these are points of failures, and you have to test all of them. Start from the bottom, from the base, from the solenoid. If it is working, fine, start to move on. The connection between the solenoid and the terminal block, and then the relay, and then from the relay to probably you have a circuit breaker, and then from the circuit breaker to the controller. So all of these different connections might be a failing point. If all of this works how it should, so because it's not very common for the PLC program to change unless you had, for example, a surge in power, and that you might be more familiar with your industry and trams. You might have the surge in power that made some sort of a fault or a change in parameters inside the PLC, and the PLC needed to be resetted or stuff like this. But it is not common for the PLC program to change just by itself. It decided to change. It doesn't happen like this. It is based on all the connections that are coming to the PLC that is going to affect the operations of the PLC. So if everything is connected right, and you don't have any messy wirings, and you don't have any overloads, and you don't have any issues in between, then you start to look at the PLC. But the PLC is usually the last place where you might find an issue. It is all about the process itself. VSD, VLT might be, not me, it might be different people. So it might be worth checking ECT website to find when the next webinars are going to be, and this might help you. Now you're welcome, Moses. So yeah. Okay.
Oh, sorry, have you answered all the questions? I've tried to answer as many as I can on the chat because we are approaching because we are approaching the end of our webinar. So let me just turn your guys' attention quickly to the courses that are coming up for September and October. We've got 2 bachelors that are starting in September, which is industrial automation and electrical engineering. And then for next year, the next intake will be the February intake, which will be the 1st of Feb. And then the Master of Science, we've got 2 of those for October and February as well, which is the Power System Analysis and Renewable Integration, as well as the Industrial Automation and Instrumentation Control. So, as promised, I have put the link for the certificate of attendance in the chat. So if you could just copy that and fill out the survey so you can receive the certificates as well as the copies of the slides and the video recordings. And so it will be sent to your email. So if it's not in your inbox when you check your email, please check the junk or spam mail, and keep in mind the timelines that I've already told you guys. So for the for the certificate of attendance, it will be within 4 days, business days from today. And then the slides and the recording will be sent within 2 business days from today. And I guess we've got one more question. Can you answer the last questions and then we'll wrap it up? So they're saying, since SCADA systems are programmed and can be remotely controlled, how can one prevent remote intrusion and reprogramming by attackers?
Cybersecurity. Cybersecurity. This is a totally different field. We just had Jaguar and Land Rover hacked here, really, which caused billions. So again, this is not an easy or a straightforward answer. It's a lot of work, it's a lot of cybersecurity, and it's a lot of precautions that needs to be done in order to make that right. So I can't think of what could be bigger than Jaguar to be hacked, really. They were shut for a few good weeks until they resumed operations. So yeah, well, cybersecurity, totally different side of things, not my area at all. This is something related to computer science and the security of networks. So yeah, you need to look into this in a very separate, separate sector. But you should know that it is all about how can you make the network secured? How can you not just get start or opening any files, which this is what happened, I believe, with Jaguar, that some file was sent to their system and someone opened that file and something like this. I can't remember exactly. But yeah, there are lots of different precautions that needs to be done in order to make things secure. And yeah, all related to cybersecurity. Okay,
thank you for that.
Thank you, everyone.
And thank you to all our attendees. And please just check your inboxes in the next couple of days for the recordings as well as the certificate of attendance. We do appreciate your time. And if there's nothing else, Have a good day or evening or good morning, depending on where you are.
Thank
Bye.
you. Bye.